We present Flying with Photons, a method to render novel views of propagating light. We illustrate our approach with this scene of a Coca-Cola bottle that is illuminated by pulses of light from a laser. The bottle is filled with water and a small amount of milk so that the laser pulse becomes visible as light scatters to the camera. We use an ultrafast camera consisting of a scanned single photon avalanche diode to capture transient videos of this scene at 250 billion frames per second. That's fast enough to capture the motion of light as shown in this video. We synthesize transient videos of this scene from novel, moving camera viewpoints, capturing the propagation of light through the Coca-Cola bottle. We can see the light focusing near the cap, being scattered along the ground plane, and eventually being scattered to the back of the bottle. Our work is inspired by previous methods for transient videography, notably work of Velton et al., which famously captured a pulse of light traveling through a Coca-Cola bottle using a street camera. Other methods for transient imaging using time-of-flight cameras, interferometric setups, and single photon avalanche diodes, or SPADs, have also been explored. However, all previous methods were limited to single viewpoint capture. Our work is also related to techniques for rendering videos from novel viewpoints. However, these methods are designed for timescales that are long enough that the finite speed of light does not matter. In our setting, the timescales are short enough that the distance between the scene and the camera and the corresponding speed of light time delay dramatically affects the measurements. So rendering from viewpoints with novel camera scene distances requires special treatment. While Transient Nerf recently tackled novel view synthesis for LiDAR measurements, this method is limited to modeling direct reflections of light and cannot render complex effects such as multiple scattering, refraction, or diffraction. Our work renders light propagating through real scenes from moving novel viewpoints. We introduce a new neural rendering method to render complex light transport effects, and we evaluate our approach on a new multi-viewpoint transient video dataset captured with our hardware prototype. Our capture setup consists of a picosecond pulsed laser that illuminates the scene with millions of pulses of light every second. We use a single pixel SPAD and a pair of scanning mirrors to measure the precise arrival times of photons scattered from the scene. For each scan point, the photon arrival times are accumulated into a photon count histogram. After scanning, the histograms are collected into a 3D volume representing a transient video of the scene. We capture this transient video from multiple viewpoints. To render transient videos from novel viewpoints, we cast rays into the scene. Then we use a neural representation to learn two fields, a conventional density field and the transient field, a mapping from a 3D point and 2D direction to a high-dimensional discrete-time signal that represents the time-varying radiance at ultrafast timescales. That is, for every ray sample, the neural representation returns a transient with bins indexed by n. To account for the distance between the camera viewpoint and the sample point, we shift each transient in time by the corresponding speed of light time delay. If this delay were not explicitly modeled, the representation would need to memorize the camera scene propagation delay from each viewpoint. We then apply volume rendering to composite the sampled transients together. The representation is supervised by minimizing the difference between the rendered and captured transient videos. To capture transient videos from multiple viewpoints, we build an imaging setup consisting of a turntable on which we mount the scene. The light source is also mounted here to be stationary with respect to the scene. We mount the scanning SPAD on an elevation arm. Here, we show a time lapse of the acquisition procedure, which typically requires 20 to 30 minutes per viewpoint, and we capture 45 or 75 viewpoints per scene. We first show this simulated scene from a static camera viewpoint. It contains a refractive object and two peppers illuminated by a point source of light. To more clearly visualize transient videos, we composite the transient over an intensity image created by integrating the transient video over time. We compare to transient videos rendered from a novel view with Transient Nerf. which only models direct components of light and fails to capture indirect effects. K-planes, which does not model propagation delays and so struggles to synthesize scene appearance from novel views. Our approach without propagation delay modeling, which similarly fails, and the proposed approach which outperforms the baselines in terms of image quality and accuracy of the recovered transient as shown in the paper. We see similar trends for this scene when rendered from a moving viewpoint. This simulated scene contains a point light source and a refractive object placed in participating media. Similar to the previous scene, K-planes and the proposed method without propagation delay modeling fail to properly account for the camera-to-scene distance of this novel viewpoint. This captured scene is illuminated from the side by a point source created by placing a diffuser in front of the pulsed laser. We omit transient nerve from this comparison because it does not handle indirect effects. Our approach outperforms the baselines in terms of image quality and accuracy of the synthesized transients, as shown in the paper. Here, the scene consists of a tank of cloudy water in which we place a mirror and a diffuser. We illuminate the scene with a collimated laser beam. We can observe the specular reflection of the laser pulse and scattering off of the diffuse target. We show another variation of this scene with a diffraction grating and visualize the light pulse being separated into the 0th, 1st, and 2nd order diffraction modes. Finally, we show a scene consisting of a mirror, statue, and multiple other objects. Our method faithfully renders videos from novel viewpoints containing specular reflections and multiple bounces of light. We can also visualize the entire transient in a single image. The hue indicates the time at which the peak intensity is observed at each pixel, and the brightness corresponds to the magnitude of the peak intensity. We modulate the brightness over time to create dark bands corresponding to isochrones, or equitime paths. Using our rendering technique, we can extend the time warping procedure of Velton et al. For novel view synthesis. This first visualization shows the appearance of the transient videos from a moving viewpoint. Here, we shift the rendered transients to remove the propagation delay from the scene to the camera based on the depth predicted by our representation. This removes the viewpoint-dependent appearance of the transients and makes the visualization more intuitive. We show another example on a captured scene. Note that without warping, the wavefronts exiting the Coke bottle propagate along the ground plane and travel away from the camera. With depth-based warping, the wavefront scatters uniformly in all directions from the ground plane. Finally, we demonstrate rendering transient videos of direct and global components of light transport for this captured scene. This procedure involves estimating direct and global components for each transient video and then retraining our neural representation separately on the direct and global multi-viewpoint transient videos. Here, we observe that the direct component captures the bright diffuse and specular reflections of light from the scene. We see indirect reflections in the global component, and the candles appear bright because of the strong subsurface scattering component. In summary, we present the first method for flying with photons, demonstrating transient video synthesis from novel viewpoints. We envision many potential avenues for impact, including for applications related to education, art, scientific visualization of ultrafast optical phenomena, and inverse rendering. Thus, our method may be useful for applications in computer vision and beyond.